Alright, let's have a sound intensity problem here with some actual values. So we are listening to a sound, forget the context, I don't care, but we're listening to a sound, and we're hearing it at a sound intensity level, so a level of decibels, I'll call it beta 1, of, oh geez, I don't know, we're hearing 30 decibels. And we are currently, say, how far away? I don't know, 30, that's the same, 20 meters from the source. So we'll have our distance be 20 meters away. Yeah, I'm going to call that R for reasons that will become apparent. Okay. Oops, that says 2. 20 meters away. So what I want to do is let's move closer. Let's move closer until we hear it with a strength or with a sound intensity level of, oh, I don't know, 40 decibels. So how much closer do we need to move in order to hear, how far away do we have to be? So closer than 20, right? We got to get closer so it sounds louder. All right. So this is actually quite a problem, really. There's a little bit of logarithmic math and so on. So let's get started. I know that the sound, the sources. So let's have the person standing over here. Here's a person. I think that's a person standing here, and there's a source over here, like a speaker or something. Is that what speakers sound like? So it's making this sound, right? Now, the person hears it after it travels some distance. And really the sound is going out in all directions here, in this circle of direction. Circle of sound going out in all directions here. So by the time it covers this distance, the person is hearing less of the sound because so much of the sound is going off in other directions. So that has to do with the intensity. Not the intensity level in decibels, but the intensity in watts per meter. So intensity is defined as power over area. So sorry, the units would be watts per meter squared, right? All right. And in this case, the area that the power is being distributed over, well, that is related to this distance here, R. So for this omnidirectional sound going out in all directions, we're going to have power over the surface area of a sphere, which is 4 pi r squared. That's the surface area of a sphere. I just looked it up, to be honest. Okay, so that's the situation we're dealing with here. We know that the intensity and power are related like this, right? Now, the power, well, as long as nobody turns the volume up or whatever, and we're not saying that they are, the power is going to be the same. So we can affect the intensity by changing R, right? As R increases, the intensity will decrease, as in as you get further away, it will sound quieter. But my intensity are not the numbers I was given. I was given the intensity level, so-called, in decibels. So you can go freely between these two, it's just a bit of a pain. So you can get an intensity level in decibels like this, 10 times the log of the intensity over this special number, I naught, which is 10 to the minus 12. In fact, I don't even know why they do this. You know what? I'm going to break the cycle right now. I'm just going to put the 10 to the minus 12 right in there. I've never known why they put it off to the side. Okay. So that is how you get between intensity and intensity level. Though the first thing I need to do is change my intensity that I was at, right, the intensity level I was at, 30 decibels, I want to change that into intensity in watts per meter so that I can manipulate it using the radius. So in order to do that, well, we have to do a little bit of algebra here. So I can divide over the 10, right, so beta over 10 equals log of I over 10 to the negative 12. And So this is the spot that you may not remember too well exactly how to do. Let me show you in general. In general, the log base, I don't know, a of x is equal to y. So the way this rearranges is a to the power of y equals x. Really, that's what a log is. If you look at this bottom equation, somebody at some point wanted to be able to solve for y here. I don't know why I ruined it. Somebody wanted to be able to solve for this y, this exponent, but we really have no algebraic means besides, well, the logarithm. If you put together a log like this, well, here is y, and this is how you solve for y, right? Now we're doing it the other way around in this case. And if a little subscripted number is ever omitted, like in this case, that means it's a 10. So there's an implied that it's a log base 10, and that is what your calculator does. Your log button is a base 10. So I can rearrange this using this rule that I just wrote here, and you can try it out too, but we should get 10 to the beta over 10 is equal to I over 10 to the minus 12. Okay, and so this is how we can get intensity level. Intensity level is equal to 10 to the minus 12 times 10 to the beta over 10, and this can be simplified more, but whatever, I'm done with algebra. So let's just plug in here, right? We said the beta was this first beta 1 was 30 decibels. So we'll plug in a 30 here, and that makes, let's see, 30 divided by 10 is 3, so this is 10 to the power of 3 times 10 to the minus 12 gives us 10 to the minus 9 watts per meter squared. Okay. So that is what my intensity was at first, and I want to get it down to an intensity level of 40, so I need to figure out what, if this is my beta 2 up here was 40, well, let's figure out what I2 is, right? So it's going to be a similar sort of thing, right? I2 will be 10 to the minus 12 times 10 to the 4 now. So it's 10 to the minus 8. Okay. Yep. All right, so now that I know watts per meter squared, now that I know my initial and final intensities, now I can use what we were referring to before, which was this concept of when you get further away, the radius of this sphere increases, which makes the intensity decrease. So let's see, can I get them both on screen? Kinda. Very top of the screen there is the equation I want to play with. So I know, I mentioned before that the power is staying the same. So I want to rearrange this thing for power. Let's say that this is I1 at a distance of R1. So R1, remember, was the distance that I said we were standing at, and I forget what it is, 20 meters. Okay, so let me just bring that down here. R1 is 20 meters. So rearranging the equation at the top of the screen, to solve for P, I would get P is equal to I1 times 4 pi R1 squared. Now the reason I did that is because, well, I could do the very same thing for I2. Right? Because I said that the power is not changing. All we're doing is walking closer or further away. And we're trying to find R2, how close we have to walk to achieve this power of I2, which is 10 to the minus 8 watts per meter squared. So if they're both equal to this P, that means they're equal to each other. Like that, right? And I can divide through by 4 pi and solve for R2. So I'm going to get that R2 is equal to R1 times the square root of I1 over I2. Da-na-na-na. All right, so really, ideally, we would have preferred to be given intensities in watts per meter squared in this problem, rather than being given the sound intensity level in decibels. but decibels are a fact of life that we need to be able to work with these. So there you have it. After we found the intensities in watts per meter squared, we used this concept that the power is not changing, right? So we set the two powers equal to each other and solved for R2 in terms of R1 and the change that happened in our intensity. Okay. Oh, and I guess I could plug the numbers in right at the end, actually, right? So that's 20 meters times the square root of, let's see, I1, 10 to the minus 9 thingamajigs over 10 to the minus 8 whatevers. They have the same units, right? So they're going to cancel out. And 10 to the minus 9 divided by 10 to the minus 8 is 10 to the minus 1, or 1 over 10. Times 20, so 20 divided by the square root of 10, which must be 3 point something there, 20 divided by 3 point something. I don't know, you can do the last step. Left you hanging, right? So some kind of number. But the stuff that I boxed there, that's what I like.